Section: Introduction. In this section, we discuss the growing interest in unified image generation. For example, OmniGen uses a simplified transformer design that can handle various image generation tasks without needing extra plugins or preprocessing. Recent advancements, like GEMINI 2.0 Flash and GPT-4o, have shown the potential of this area, moving us towards powerful, unified systems instead of specialized models. Other models, such as Chameleon and EMU3, use discrete autoregressive methods, while the Janus series features dual image encoders for understanding and generating images. Transfusion combines autoregressive and diffusion methods in one transformer framework. However, the tasks these models can perform are still limited. We introduce OmniGen2, an open-source generative model that performs well across many generation tasks. Unlike the original OmniGen, we found that simply sharing parameters isn't enough for managing both autoregressive text and diffusion-based image tasks. Therefore, OmniGen2 uses separate pathways for these tasks. While models like GPT-4o are good at following prompts, they often lack the consistency needed for precise image editing and maintaining subject identity in context. We believe this inconsistency stems from models relying solely on high-level semantic encoders, which struggle to capture the detailed visual elements needed for these tasks. To fill this gap, OmniGen2 builds on its predecessor by using variational autoencoder (VAE) features for low-level visual information. Recent models like MoGao and Bagel also use separate parameters for text and image processing and dual vision tokenizers. In contrast, OmniGen2 feeds VAE features only into the diffusion model, keeping the multimodal understanding of the large language model intact and reducing redundant image representations. This approach allows OmniGen2 to retain the simplicity and strong text generation abilities of the original model. We also address foundational data and evaluation challenges that hinder progress in this field. We began by gathering and reorganizing relevant open-source datasets, but many suffer from quality issues, particularly in image editing and in context generation tasks. This has widened the performance gap between open source and commercial models. To tackle this, we created a pipeline for generating image editing and in-context data from videos, which we plan to share with the community. Additionally, we developed reflective data for image generation through an iterative process, aiming to incorporate reasoning and reflection from large language models into multimodal generation. Our evaluation of OmniGen2 shows it performs competitively across various tasks, including text-to-image generation, image editing, and in-context generation. However, there is currently no established public leaderboard for assessing in-context generation capabilities systematically. Existing resources like DreamBench do not adequately capture the complexities of real-world scenarios. To address this, we introduced the Omni Context Benchmark, which includes 8 task categories designed to evaluate consistency regarding individuals, objects, and scenes. Our experiments indicate that OmniGen2 achieves top consistency performance among open-source models. In summary, our main contributions include the open sourcing of OmniGen2, a robust multimodal generative model excelling in various image generation tasks while maintaining strong text generation capabilities. We also explore multimodal reflection mechanisms in image generation, develop new data generation pipelines, and create high-quality datasets from videos to address data scarcity. Lastly, we present the Omni Context Benchmark, a comprehensive evaluation suite for assessing in-context visual generation capabilities. It's important to note that the text generation ability in OmniGen2 primarily comes from the large language model component in its decoupled architecture, rather than from direct end-to-end training of the model, except for a special token. Full parameter training occurs only in the reflection model. Thus, we view OmniGen2 as a multimodal generative model that can produce both images and text simultaneously, rather than a fully integrated multimodal model. In the original OmniGen framework, we used autoregressive modeling for text and a diffusion approach for image generation, both within a transformer architecture initialized with PHI-3. After releasing OmniGen, we conducted further experiments. We replaced PHI-3 with the more powerful Qwen model, but surprisingly, the image generation quality declined despite using a stronger large language model. We also tried a mixture of expert strategy to route text and image parameters independently, similar to LM Fusion. Our findings showed that initializing the image branch with parameters from the text branch resulted in poorer performance compared to random initialization of the image pathway. This suggests that text-optimized parameters are not suitable for image modeling. As a result, in OmniGen2, we decouple the diffusion process and randomly initialize its parameters. Recent methods like MetaQuery and Blip3o use learnable query tokens to encode conditional information for diffusion generation, but this can limit representation capacity and lead to information loss. We found that token-based compression struggles with long text rendering. Therefore, OmniGen2 uses the hidden states from the multimodal interleaved conditions produced by the large language model as input to the diffusion decoder, rather than relying on a fixed set of learnable query tokens. We may explore integrating both hidden states and query tokens in future work. Another key consideration is the use of the VAE encoder. While existing large language models mainly use vision transformers, VITs, for image modeling, VITs often fail to capture fine visual details, leading to lower image quality in generation tasks. Although end-to-end training of VIT features can help, it complicates balancing image understanding and generation. Recent works like Bagel and Mogao address this by encoding images twice with both VAE and VIT features, but this requires significant architectural changes and complex attention mechanisms, increasing development difficulty. Adapting to this new architecture also necessitates retraining to restore image understanding capabilities. Given these challenges, we choose to use VAEs solely as inputs to the diffusion decoder, rather than integrating them into the large language model. This approach maintains the architectural simplicity of the large language model and preserves its multimodal understanding abilities without extensive retraining. Section Summary. In this section, we introduce OmniGen2, an open-source generative model that enhances image generation capabilities by employing distinct architectural pathways for autoregressive text and diffusion-based image tasks, addressing limitations in consistency and detail capture found in previous models. We also present the Omni Context benchmark for evaluating in-context visual generation and outline our efforts to improve data quality for advanced image editing and generation tasks. Section: Multimodal Large Language Model. In this section, we describe our approach to the Multimodal Large Language Model, MLLM. As shown in the figure, we utilize a foundational MLLM transformer that can handle both text and images. For generating text, we use an autoregressive language head, while image generation is done through a specific diffusion module. We initialize the transformer backbone with Qwen 2.5-VL3B and introduce a special token, less than, img, greater than, to signal when an image should be generated. When the model sees this token, it activates the diffusion decoder to create the corresponding image. The hidden states from the MLLM act as inputs for the diffusion decoder, but since these states may not contain enough visual detail, we enhance the decoder with features from a variational autoencoder, VAE, derived from the input images. The diffusion decoder then produces images using a rectified flow method. Next, we implement a straightforward diffusion transformer architecture that combines features from the MLLM, VAE, and noise, allowing for joint attention across these different types of data. Following the Lumina Image 2.0 approach, we first process multiple input conditions through a refiner network to ensure they align before they enter the transformer layers. Our diffusion decoder consists of 32 layers with a hidden size of 2,520, totaling around 4 billion parameters. By incorporating VAE features, the hidden states related to images in the MLLM become less important, so we eliminate those states and keep only the text-related ones. We also use a 3D rotary position embedding in the diffusion transformer, which modifies the Qwen MROPE. We introduce a new Omni rope for multimodal rotary position embedding, tailored for our complex tasks like image editing and in-context generation. As depicted in the figure, our Omni rope has three components: a sequence and modality identifier that distinguishes tokens from different modalities and sequences, treating each image as a complete unit with a shared ID for its tokens, while text tokens have a sequentially increasing ID. The second component is a 2D spatial height coordinate that indicates the vertical position of image tokens, and the third is a 2D spatial width coordinate for the horizontal position. For non-image tokens, both coordinates are set to 0. This design ensures that tokens in the same position share the same spatial embeddings, promoting consistency during editing. The sequence and modality identifier helps differentiate between various image entities, and our M rope can adapt to standard 1D positional embedding for text-only inputs, making it a versatile framework for multimodal tasks. For our training strategy, we initialize the MLLM with Qwen 2.5-VL, keeping most parameters frozen to maintain its multimodal understanding. We only update the new special tokens. The diffusion model is trained from scratch, starting with the text-to-image generation task and then using a mixed task strategy for various objectives. During the reflection training phase, we unfreeze all model parameters, allowing the model to create reflective text descriptions and refine image outputs iteratively. In terms of dataset construction, we use the dataset from LLaVA1 Vision for multimodal understanding tasks. For text-to-image generation, our training set includes about 140 million open-source images from various sources, along with 10 million proprietary images for which we generate synthetic annotations using Qwen 2.5-VL72B. For image editing tasks, we gather publicly available datasets, but these often have issues like poor image quality and limited task diversity. To address these challenges and better meet our research goals, we have carefully built a new comprehensive training dataset, which we will detail in the following sections. Section Summary. In this section, we describe our multimodal large language model, OmniGen2, which integrates a transformer architecture to process both text and images, utilizing an autoregressive language head for text and a diffusion module for image generation. We also introduce a novel Omni rope for effective multimodal position embedding and outline our training strategy, which includes a comprehensive dataset construction to enhance model performance across various tasks. Section: In-Context Data. In this section, we focus on the in-context image generation task, which involves extracting a visual concept, like a specific object or individual, from input images and accurately reproducing it in newly generated images. This process, known as subject-driven generation, is similar to in-context learning in large language models. Our image generation model creates personalized outputs in real time based solely on the provided context, without needing extra fine-tuning. Although in-context image generation has been widely studied due to its many applications, we still face a significant lack of high-quality datasets designed for this task. For in-context generation, we need to model how an object appears in various scenarios. To do this, we utilize video data, which captures the same subjects under different conditions across frames. This temporal diversity allows us to create training pairs where subjects remain consistent in meaning but vary in pose, viewpoint, and lighting. Our data pipeline starts by extracting keyframes from each video and selecting a base frame. Using a specific model, we identify the main subjects in the base frame, focusing on important entities while ignoring irrelevant background objects. We then obtain subject bounding boxes based on tags generated by the model. Next, we use another tool to segment and track these subjects in subsequent frames, ensuring we select the last valid frame that includes all subjects to maximize appearance variation. To reduce tracking errors, we introduce a filtering step to maintain subject consistency. To enhance visual diversity, we outpaint the subject with a new background in the input frame. We also filter out samples where the subject's appearance varies too much and assess the quality and consistency of the generated samples. Additionally, we generate concise object descriptions and detailed captions for the base image, which we integrate into natural language instructions. The final training triplet consists of the instruction, the repainted image as input, and the original image as output, providing rich and diverse supervision for multi-subject generation tasks. We also extend this in-context generation approach to editing tasks, introducing in-context editing. In this task, we extract relevant elements from a context image to edit a target input image. The data source for in-context editing is similar to that of in-context generation. We select two frames with the same object, one as the context clip and the other as the target clip. We obtain object masks for both frames and apply outpainting to the context image to create a new background, helping the model focus on object-specific features. We then inpaint the target clip, removing the object while keeping the original background to create the input clip. Finally, we generate a natural language description of the transformation from the input clip to the target clip, combining it with the object description from the context clip to create comprehensive instructions. While most existing editing datasets are built using inpainting techniques, they often suffer from low image quality and inaccurate editing instructions. To overcome these issues, we select a small set of high-quality images from text to image data and apply inpainting. We use the inpainted images as inputs and the original images as targets to ensure high-quality results. We do not provide instructions to the inpainting model, allowing it to fill content randomly. After obtaining image pairs, we use a machine learning model to write editing instructions based on these pairs, resulting in a high-accuracy editing dataset. Traditional inpainting methods struggle to create diverse data types, making them inadequate for tasks like action modification or object movement. To address this, we extract editing pairs from video sources. We segment videos into distinct scenes to avoid pairing frames from different contexts. We detect scene boundaries by analyzing average pixel intensities and use a rolling average of color differences to enhance robustness. Within each scene, we extract multiple frame pairs and evaluate their differences. We filter out pairs with significant viewpoint changes or negligible differences. Since camera viewpoints can change even within a scene, we further refine our selection by comparing color histograms of image blocks to assess similarity, which helps reduce noise impact. We calculate the proportion of similar blocks to ensure viewpoint consistency. For each retained image pair, we generate precise editing instructions, facilitating the creation of high-quality image editing datasets. Section Summary. In this section, we describe our approach to in-context image generation and editing, which involves extracting visual concepts from input images and generating new images or editing target images based on context. We utilize video data to enhance diversity and consistency in our training datasets, while also addressing limitations in existing editing datasets by employing high-quality images and advanced models to generate accurate editing instructions. Section: Interleaved frames. In this section, we segment videos by identifying scene transitions and extract keyframes from each segment. We then create two types of video frame sequences, each containing up to 5 frames. One sequence includes frames from the same scene, while the other includes frames from different scenes. After extracting these sequences, we annotate each pair of consecutive frames with descriptive captions using a multi-language large model to highlight changes in object actions, environmental variations, and differences in object appearances. Due to the large number of annotations needed, we utilize a lightweight model, Qwen 2.5-VL7B Instruct, for this task. As a result, we gather 0.8 million interleaved data samples from video sources to pre-train the model for processing continuous multimodal sequences. Next, we draw inspiration from recent advancements in test time scaling and self-reflection in large language models to explore how these reflection capabilities can be integrated into multimodal generation models. We demonstrate that test time scaling can improve image generation quality. Our reflection data consists of an interleaved sequence of text and images, starting with a user instruction, followed by the model's generated image and reflections on the previous outputs. Each reflection focuses on 2 main points: analyzing shortcomings related to the original instruction and suggesting solutions for the identified issues. To create self-reflection data, we select a small subset from the training data, specifically from the text-to-image task, and generate images using the model. We then use a multi-language large model to evaluate if the generated images meet the instruction requirements. If the images do not adequately follow the instructions or have quality issues, the model identifies errors and proposes changes. Initially, we used the DSG evaluation framework to assess instruction image alignment, but this often led to inaccuracies. We later found that powerful multimodal models could handle this task directly, so we switched to using DOUBAO 1.5 Pro for identifying issues and suggesting modifications. After the first round of reflections, we combine the generated images and reflections with the original instructions and fine-tune the model on this data. Once training is complete, we continue to generate data using the first round of reflection data to obtain a second round of images and reflections. This iterative process results in multiple rounds of self-reflection data. We note that there is limited research on using reflection mechanisms to improve image generation in multimodal generative models, and we hope our work will advance reasoning capabilities in this area. After the model develops initial reflective abilities through training, we plan to explore online reinforcement learning algorithms to further enhance these capabilities in the future. For the Omni Context benchmark, our main goal is to enable consistent generation of specific context images as provided by users. To evaluate this important yet under-researched capability, we introduce Omni Context, a new benchmark that assesses a model's ability to maintain subject fidelity across various contexts. Current benchmarks for in-context image generation do not adequately reflect real-world scenarios, as they often overlook situations with multiple input images and are limited in the number of context images and task types. For instance, DreamBench includes only 30 objects and 25 prompt templates, lacking coverage of human subjects and scene-level contexts. Previous benchmarks have also relied on metrics that assess image-level similarity, which are insufficient for scenarios with multiple subjects and lack explainability. To address these gaps, we create Omni Context using a large, manually collected dataset of high-quality images, including personal photos, open-source images, animation stills, and AI-generated images. The benchmark features 3 categories of context images: character, object, and scene, covering a wide range of entities and environments. We establish 3 main task categories: single, multiple, and scene, along with 8 detailed subtasks, each containing 50 examples. The single category involves generating images based on a single context image featuring either a character or an object. The multiple category focuses on interactions between subjects from multiple context images, while the scene category pertains to image generation tasks based on specified environmental contexts from reference images. We adopt a hybrid approach for constructing image prompt pairs, combining multimodal large language models and manual annotation. Initially, MLLMs classify and filter image sources to eliminate low-quality samples. Human experts then curate the remaining images based on 3 criteria: clear depiction of the main subject, aesthetic quality, and diversity. Prompts are generated using GPT-4o and are subsequently refined by annotators to ensure diversity in both content and structure. To evaluate in-context image generation and improve the explainability of the results, we use the advanced multimodal large language model GPT-4.1 to assess the generated outputs. Omni Context includes 3 metrics: prompt following, subject consistency, and an overall score, which is the geometric mean of the first 2 scores. Following the VI-score methodology, we use GPT-4.1 to generate scores on a scale from 0 to 10, providing detailed justifications for its evaluations. We believe that the Omni Context benchmark will be a valuable resource for advancing research in controllable, reference-based image generation. Section Summary. In this section, we describe our approach to video segmentation and frame extraction, creating interleaved sequences of frames for annotation with descriptive captions using a lightweight model, resulting in 0.8 million data samples for model pre-training. We also introduce the Omni Context benchmark, designed to rigorously evaluate a model's ability to generate context-specific images, utilizing a large-scale dataset and advanced metrics to enhance the explainability of image generation tasks. Section: Experiments. In this section, we conduct a thorough evaluation of OmniGen2 to showcase its unified capabilities across various generation tasks. We start by comparing it to leading models in a table that includes four main areas: visual understanding, text-to-image generation, image editing, and in-context generation. Our findings reveal that OmniGen2 performs exceptionally well across all domains, particularly excelling in in-context generation. For visual understanding, we utilize a pre-trained model with 3 billion parameters, known as Qwen 2.5-VL3B Instruct. Our results indicate solid scores of 79.1 on MMBench, 53.1 on MMMU, and 61.8 on MVet. Freezing the model helps maintain its strong understanding abilities without degrading performance during training. Additionally, the smaller model size makes OmniGen2 more efficient and easier to deploy. In text-to-image generation, we evaluate OmniGen2 on two benchmarks: GenEval, which tests compositional understanding, and DPG-Bench, which assesses long prompt following. Our model shows competitive performance, especially in terms of resource efficiency. On GenEval, OmniGen2 achieves a score of 0.86, surpassing other models like Uniworld v1 and coming close to the top model, Bagel. Notably, we achieve this with only 4 billion trainable parameters and a smaller dataset compared to Bagel. On the DPG bench, OmniGen2 scores 83.57, outperforming Uniworld v1 and competing closely with specialized models. These results confirm that OmniGen2 is a capable generator for both complex and general prompts. Image editing is another key strength of OmniGen2. We evaluate its performance across three benchmarks: EmuEdit, GetItBenchN, and ImageEditBench. Our results show that OmniGen2 excels in instruction-based editing, achieving the highest score on EmuEdit for applying edits effectively while maintaining the integrity of unedited areas. It also ranks highly on GetItBench, although its performance in specific tasks like portrait beautification and text modification is lower due to limited data. Overall, OmniGen2 stands out as a leading open-source model in image editing. In-context generation, we introduce the OmniContext benchmark to assess performance in this area. OmniGen2 sets a strong baseline with an overall score of 7.18, demonstrating its ability to accurately separate subjects from backgrounds and follow new instructions. It consistently outperforms other open-source models and shows significant improvements over competitors in various tasks. While closed-source models like GPT-4o and Flux.1 Context perform well in certain metrics, OmniGen2 remains a strong contender across the board. Section Summary. In this section, we conduct a comprehensive evaluation of OmniGen2, demonstrating its strong performance across various generation tasks, particularly excelling in context generation. Our results reveal that OmniGen2 achieves competitive scores in visual understanding, text-to-image generation, and image editing, while maintaining efficiency with a lightweight model architecture. Section: Reflection. In this section, we fine-tune OmniGen2 using the reflection dataset and showcase its reflection abilities. We observe that in successful cases, the model reflects on the initially generated image, recognizes its flaws, and makes necessary adjustments in the second round, resulting in an image that meets the given instructions. Additionally, the model can appropriately end the generation process. Our findings suggest that the fine-tuned model excels at correcting issues related to object color, quantity, or shape in the initial image. However, we also identify significant limitations during both the reflection and correction phases. The model may over-reflect, especially with simple instructions, leading to unnecessary requirements or incorrect conclusions. At times, it fails to revise the image based on its reflections or follows flawed instructions, resulting in poorer outputs. These challenges arise from the limited perceptual abilities of the current 3B scale multimodal large language model, MLLM, and a lack of diverse reflection training data, which can introduce biases. In future work, we aim to scale up the MLLM and investigate reinforcement learning methods to improve the model's reflection capabilities. We also recognize several limitations of OmniGen2. First, there is a performance gap between English and Chinese prompts, with English generally yielding better results. For example, a Chinese prompt may lead to minor inconsistencies between the input and edited images. Second, the model struggles to modify human body shapes, likely due to a lack of real-world data capturing such variations. Third, the quality of the generated output is highly dependent on the input image quality. Low-quality images lead to significant degradation and loss of detail. Fourth, the model performs better when prompts clearly specify the relationship between objects and their source images, indicating sensitivity to ambiguous multi-source instructions. Lastly, in in-context generation tasks, the model sometimes fails to accurately reproduce objects from the provided context. While increasing the guidance scale can help, it does not fully resolve the issue. We believe that substantial improvements in these complex tasks may require further scaling of the model. In terms of image generation, diffusion models have shown great success in creating high-quality images. Notable systems like Stable Diffusion, DALL-E, and Imagine have established strong text-to-image capabilities, paving the way for more controllable and scalable generation. To improve controllability, models such as ControlNet and T2I Adapter add external condition modules, while others focus on detailed editing and instruction-driven generation. Recently, there has been a shift towards unified image generation, which aims to manage various tasks within a single model. OmniGen achieves this by jointly modeling text and images in one transformer. Some approaches treat different tasks as video generation predictions, using distinct prompts for differentiation. Although chain-of-thought reasoning has been introduced to enhance image generation, research on reflection mechanisms in this area is still limited. Reflection Flow proposes a framework that combines several components, including the original text-to-image model, a fine-tuned MLLM for instruction generation, and an image editing model, requiring training only on single instruction image pairs. In contrast, OmniGen2 takes an integrated approach, allowing for reflection and image regeneration within a single model, and is fine-tuned on multi-turn reflection data to better capture the iterative nature of real-world image editing.